Right. Good afternoon, everyone. I hope you're having a great summer so far. So, my name is Jean-Michel Tin, and I serve as a cybersecurity coordinator for the National Center for Transportation Cybersecurity and Resiliency, better known as TraCR. So, TraCR is a US DOT-funded National University Transportation Center led by Clemson University in collaboration with 9 other prestigious universities around the nation. The director of the center is Dr. Ronnie Chaudhary. So without further ado, I will leave the floor to Dr. Chaudhary.
Thank you, Dr. Swami, for being our speaker today. We are really delighted about it and honored. Here's a short bio about our speaker, Dr. Swami. Mansha Swami is a research engineer at the National Transportation Center at Morgan State University in Baltimore. Over the past 15 years, she has worked extensively in the academic and research areas in transportation, previously serving as an assistant professor of teaching undergraduate and graduate courses in transportation and civil engineering. And also she conducted research at the University of Texas and Arlington in addition to teaching. Her current research is supported by the U.S. Department of Transportation and the Maryland Department of Transportation, spanning applications of AI automation in transportation and identifying use case metrics, road safety studies, mobility and impact assessment, cybersecurity in transportation, human factors, driver behavior, mental health impacts on drivers, transit rider experience, efficiency evaluation, and dynamic behavior in transportation systems. It's my honor to request Dr. Mansi Swami to present her talk for today, which is investigating driver behavior under cyber attacks in a connected vehicle environment. Dr. Swami.
Thank you so much, Dr. Chaudhary. Thank you so much. I am sharing my screen. Are you able to see the screen?
Yes, we can see it. We can see it.
Okay.
How about the other audience? So, Stephen, can you see it? The screen?
We can see
absolutely, yes.
All right. Okay, thank you. Thank you for confirming. So today I will be talking about the topic investigating driver behavior under cyber attacks in connected vehicle environments. So at Morgan NTC, we do a lot of work in connected vehicle environments, and we also have a connected vehicle test bed. There have been a lot of driver behavior studies that as a research group we have done in the past. So this project was submitted to TraCR for as a competitive proposal, and we started it in collaboration with Clemson University. I have my team as follows. The PI of this project is Dr. Mansoor Jehani, who's also Director Smarter in NTC Center. Myself as co-PI, Dr. Ehsan Mehryar, my colleague as co-PI, and also our Clemson collaborators, Dr. Shubham Agarwal and Dr. Dustin Souders. So we tried to look at 2 different aspects of cyber attacks. One aspect is the IT part, where the networks get affected and where different firewalls are there needed to take care of how to protect these cyber attacks from happening inside the vehicle or over a connected vehicle environment. So we decided to not look in that direction, but try to focus our understanding only on what kind of driver behavior response and human factors at large are at play when we try to see the cyber attacks. How can they be studied in aspect of how the driver responses to that? And then within the connected vehicle environment, we decided we would select those ADAS features which people are most familiar with, like blind spot warning, forward collision warning, all of those. So this project is having 2 phases, and one phase is going on right now. The first phase, the data collection ends in the next week, and therefore we will be analyzing it. And the second phase will be expanding the scope of this project into several other features. So when we were studying about several reports on the fact that you must have heard about it. In 2015, there was a set of hackers and researchers, Mr. Miller and Mr. Walasek, who decided to expose the vulnerability of the Jeep ecosystem using their Uconnect and entertainment systems. And they could get control of that using the car's own internet and the mobile cellular mobile networks. And they could go to as much as mishandling and handling and controlling the brakes, the windshield wipers, the infotainment system. So all of that they explored. And after that, when the company decided to investigate more into these vulnerabilities, they figured out that their cars in the categories of the models in Dodge, some in Chrysler, and some in Jeep Cherokee were very much vulnerable to this kind of attack if it happens again, if someone takes over the remote control of the vehicle. So they recalled 1.4 million vehicles in that particular after that particular incident. Similar incidents happened when researchers from the Keen Lab tried to look into how they can get access into the infotainment system and the physical infrastructure like locking of the gates and all of that with Tesla Model S in 2016. And also in BMW, when they investigated their internal systems, they figured out there are 14 different types of vulnerabilities which their vehicle is exposed to in that particular research that they did in their internal investigations. So our understanding was that if we try to look at the bigger figures of how many connected vehicles are we expecting to be projected in 2030, so most of our passenger vehicles and even our freight vehicles may expand to the connected vehicle segment. And also, most of these OEMs are already coming in with some kind of inbuilt OBU features. Very few of them have it currently for the inbuilt OBU, but they're expanding. And for the SAE level 1 and 2, most of our newer conventional vehicles on the road, they do have those ADAS safety features as well. And when we look at the involvement of human driver in this entire picture, this can be very directly connected with the data that we have from an NHTSA published for the 2023 vehicle fatalities, in which they attributed 93% of these accidents and crashes to have human error in them. So when we look at this bigger picture, we look at our problem selection that in the direction of why we decided to investigate further into how these human factors affect the driver behavior and in turn uh, give a different response from the drivers when they are subjected to a cyber attack scenario. So there are several aspects to understand the research gaps. We have done a very extensive literature review, and I will be discussing that in the upcoming slides. But if you look at the human factor side of this particular problem, most drivers misattribute these attacks as either ADAS feature malfunction or some kind of system glitch or some kind of network glitch. But we have collected data for 90 participants so far, and so far none of them was able to attribute it to a cyber attack possibility. Uh, they also have expressed over trust in the ADAS features. And over the time, when these ADAS safety warnings are displayed on your dashboard or you hear the audio signals, there is a chance of getting over habituated to these repeated warnings. And so till now, even in the driving simulator and driver behavior testing, a very limited set of researchers have worked on the ADAS coverage patterns, leave alone looking at it from the human factor side and understanding the driver behavior. So this is a first of its kind study. There have been some studies understanding the driver simulator and the vehicle performance aspects of it, but this is the first of its kind study in the human factors orientation. And these both the simulators at Morgan State and at Clemson universities are used in conjunction. And we are looking at the urban scenario, urban networks at the Morgan State, and we are looking at the suburban networks at the South Carolina Clemson University simulator. So we have created different networks uh, for both the universities, and then our intention is to study both the urban and suburban environments um, in this. So the main objectives of this project was to investigate how the driver dispositional factors like trust in driving style and tech savviness and ADAS familiarity influence the detection of cyber attacks. And then we want to understand how this performance of this person driving this vehicle, which is subjected to a false cyber attack situation or a true cyber attack situation, is behaving based on the V2X information it receives from this vehicle. And then we want to compare these driver responses across the urban and across the suburban environments. So for the first phase, we decided to pick up only one of these features apart of a set of four that we selected initially to explore. So initially we started with TIM messages, traveler information messages, the phantom signals testing, timing, and the blind spot warnings and the forward collision. So we decided let's stick to just one blind spot warning and let us try to investigate deeper into how blind spot warning is looking at when we try to go ahead with our objectives. So in phase two, we expand to the other three features as well. So the conceptual framework of this study relies in three types of layers. One is the attack layer, when we falsify V2X channel inside the vehicle and network, and we try to see how we can introduce information that misleads the driver. This information is displayed and given to the driver through the information layer on the human machine interface, mostly our dashboards. We have used an audio as well as flashing message based information. And then we look at the driver layer, how the driver perceives, what is the attribution, what is the response, and then when we finally analyze the data, then the outcome of it. So this study is going under data collection. So we are just understanding how these drivers are responding at the present state. So we want to see how much trust do they have in the CV technology, what is the driving style, what is the tech savviness, how much ADAS familiarity they have before they participate in this study, and what is the reliance on those ADAS features. We also try to understand which environment they are driving in, either it's urban or suburban, and the understanding from the cybersecurity aspect and the demographics. That is the basic. So when we understand the literature, we have segmented it in three parts. One is the cyber attack taxonomy on connected vehicle. You can see a vector diagram on the right-hand side. There are several vectors described in here which can be used to be targeted in a way that the vehicle can be attacked, and these all vectors can be affected. So one of them can be your tire pressure monitoring system, the other one can be your remote attack, which can impact your system in your infotainment, and then they can impact your sensors by taking control over your sensors. They can take control over your head unit and take control of your wireless Bluetooth, and then be a middleman in this entire cyber attack picture. And then they can also be introducing some kinds of civil attacks and some kind of attacks in your physical infrastructure of your vehicle, such as just basic locking and unlocking of your doors, your windshield wipers, your braking mechanisms, all of that. So they can be in-vehicle attacks and electronic control unit tampering, and they can be second layer, which is the V2X communication threats, the Sybil, the replay, the detection of services, the middleman, and the GPS spoofing. They can be the application and interface, which mostly goes with the infotainment exploits, but also with OVU and the mobile app weaponization. Then you have false data injection attacks, which false data can be relayed over and information can be compromised. So our selection of the ADAS feature, which is the blind spot warning, it comes at an intersection of layer 2, which is the V2X communication threats, and the data-oriented attacks. So these two make up somewhat the cluster of vectors that we want to look at when we try to understand the driver's response. And when we try to understand where in the past literature have people tried to study what a corrupted blind spot warning looks like and what factors were studied on that blind spot warning, we tried to look at the literature. We found some studies. You can see on the screen 6 previous studies conducted in where the attacks were false data injection, the replay attack, the spoofing of safety messages, the denial of service, the Sybil attack, and the GPS spoofing. And out of these 6 studies that were conducted in the past, 4 were attributed to false positive kind of attack. The denial of service or the suppression was attributed to the false negative. I will come to explain what exactly we are meaning by when we say a false positive or a false negative in a next slide. And then in the Sybil attack, it can go either ways depending on the intention of the hacker. So these are the different design theories which can happen based on these different attacks. So when we look at the other literature from the human factors gap point of view, we also have several researchers who have worked on drivers' perception of cyber attacks, cyber knowledge, and response under unexpected attack. Then they try to train and warn the systems, some ransomware attacks. Then they try to see what different driving styles in disposition, null moderators, and risk perception. And then Ben and Asher did a study in 2015, which tries to understand if the knowledge of having cyber attack induced in your vehicle, if having that kind of knowledge improves detection or does not improve detection. And then if it improves detection, does it still improves the driving behavior or not? So these are different types of studies which have taken in the past in understanding driver behaviors. Most of them were understanding driver behavior in the cyber attack response. Some of them were trying to understand driver behavior under the cyber attack situation, but none of these studies expanded to the connected vehicle ecosystem and then to the ADAS safety features and then further looking at the human factor side of the driver response. So the gaps in these are they firstly have very narrow ADAS coverage and no clean signal detection theory framing, and there was no cross-site replication. And so these studies, some of them were conducted on driver simulators, but not covering the entire gamut of attributes that we are looking into. When I was discussing about the false positive, false negative, true positive, and true negative scenarios, this is what it actually looks like. So if you have an alert in your vehicle when there is a blind spot situation, when another vehicle is in your blind spot and your vehicle gives you an alert, that's a true positive. That's actually happening real time. And when there is no vehicle present, but your vehicle still gives you a warning that there is a vehicle in your blind spot, that calls as false positive. In false negative, there is no vehicle in your blind spot, and the system doesn't even informs you about that. So that's the base default system which our driving is designed for when there is no vehicle in your blind spot and your vehicle never gives you any kind of alert. But there can be a situation where there is a vehicle, there is no vehicle in your blind spot, and you still get those warnings. So these are all the different types of ways in which we are trying to understand. We have introduced these different warnings at several stages in our network, and then we are trying to see how we get the response. And the reason why we selected the blind spot warning in the first iteration of our experimentation in this direction is because it is a very high frequency safety feature. It happens very often, and then it happens in a way that uh, you are expected to change your lane. So it's very, very discreet in the form of its trigger. And either your vehicle in the blind spot is present or not present. There is no third possibility there. So it is easier for the driver to react to and attribute it. It's very cleanly classifiable. And the false positive is not something that can make a driver maneuver the vehicle in a way that can cause a critical situation. And so these are the reasons why we decided to choose the blind spot warning. We also understand that it is important for us to introduce scenario trigger points, which are based on deception design, which means we have not told our driving participants before the driving experience that they will be looking into understand the cyber attack potential of this exercise. They only understand they are driving on this simulator to understand the ADAS safety features and how efficiently these ADAS safety features are working or not working. There can be several possibilities which are open to them to guess if they feel there are some kinds of warnings which are not working for the way that they were designed to work. But we do not tell them before the experiment finishes. And there are some warnings which are false negatives and false positives. And mostly some of the false positive warnings come after the true positive warnings, and the drivers are confused. We can pretty much identify during the experiment, but so far 90 drivers have completed this experiment, and but they are not able to figure out in the post survey about how it looks like, in is there any possibility of a cyber attack. So the knowledge and awareness about a potential cyber attack is also something that we are looking at running low. This was another cyber attack which we were trying to look at, which was the forward collision warning. But when we decided to finally inculcate inside our experiment for the pilot, we decided to go with only the blind spot warning. And we were predicting driver responses as sudden braking on clear roads and lane change, abort, and hesitation, and then their discomfort with the idea of a blind spot warning displaying on their dashboard. But when they're checking in their rear mirror, there is no vehicle. And so in the future, when an actual true positive blind spot warning happens, they have very reduced confidence in the occurrence of a true incident. So even after the true negative, when the true positive situation arises, they tend to ignore that warning at a couple of instances. So they either trust the system too much, and or either they start distrusting the system because of continuous different types of warnings popping up on their dashboards. So and this was the methodology sequence that we followed. So we first understood the scheduling of the participant, then they were given the informed consent. They were introduced to the V2X concept by showing a video on the CV technology, which is there on our YouTube channel also. There were some pre-study surveys. We wanted to understand human-computer trust values for them on a Likert scale, some driving styles, some different ADAS features, how much they are familiar with, the demographic. Then there was a base scenario in which they were driving only to get comfortable with the simulator. This is not the scenario we are collecting data for. Then they drive the control scenario in which we only have true positive warnings. There is no confusion. They get a blind spot warning. They have a vehicle in their blind spot. In the second scenario, when we introduce the cyber attack, they have false positives and they also have false negative interjections. Then again, we asked them to fill up a post-study survey, and we want to understand more and more how they attribute these failures in the system. And we tried to even have one open-ended question trying to investigate into if they could figure out what could have been a potential reason for this kind of misleading dashboard warning. So then once this experiment is completed, they are debriefed about what we were trying to assess from their participation. And then they are revealed about the cyber attack behavior that we are wanting to collect from them. Here is a video. I'm going to play it. I hope you'll be able to hear the audio at your end. If not, I will just tell you during the network, whenever a red box appears on the dashboard, there is an audio signaling like a sound of a beep beep along with the flashing of the red box. So I'm not sure if you'll be able to hear the audio at your end or not. So I'll just play this. So you must have observed in this video, there was one instance where the blind spot warning was given, but there was no vehicle in the blind spot. And then there was a forward collision brake warning given. At the first instance, the vehicle was there in front of you, so making a brake was needed step to be taken. But in the second brake warning, there was no vehicle in front of you. So that kind of confusion is something that we are intending to create with these experimental designs. So in our control baseline scenario, everything happens in a very ground level normal way. There is no misleading information. There is no information that confuses the driver. But in the second scenario, we have manipulated these cyber attacks. We have introduced false positive and false negative. There is no alert sometimes, but there is a vehicle in your blind spot. So those incidents are also there. And then we want to capture the different attributes related to their driving behavior. And this study happened in the same methodology across both universities at Clemson and at Morgan. The only difference being the networks are different, and the environment in which these networks have been designed are different. So, and in the pre-study survey, we want to ask them questions about what is the human-computer trust scale. This has been inspired by one of the researches done by Gulati et al. In 2019, and they used Likert scale. So we used some of the questions to ask to our participants on a Likert scale basis. Then we also have some kinds of driving styles inventory. We try to understand what kind of driving style they identify themselves with. Some kind of questions about how familiar they are with the ADAS features in their vehicle, or if they are driving a vehicle with no ADAS features, or if they have a vehicle with ADAS features, but they are not familiar with that. Because when in 2023, we were talking with Maryland DOT, and they informed us they want an kind of a video to be made for them that helps users understand different ADAS features in their vehicle. Because most vehicle manufacturers, when they sell this vehicle to you, they really do not educate you about those ADAS features. So some users are aware about them, and some of them have it in their vehicle, but they don't know about those. And the basic demographic details. In the post study, we wanted to look at what are the human computer trust scale paired with the pre-score. So we understand from this post study, has there been a difference in the trust factors? Because they were given misleading information several times during this scenario. So now their trust has reduced or increased based on their personal experience. And then we want to see what kind of blind spot warning evaluation they feel, whether they feel it was given to them at the right time, what kind of safety level they attribute to this warning. And then they wanted to see their behavior changes. Then their open response questions include whether they understand that the warnings at places were not matching the road situation or anything unusual that they came across during their driving session. And then after that, we were planning to have a semi-structured audio interview with them, but most of our participants were not comfortable with that, so we had to alter that and add one more open-ended question to our studies. So we had to remove that audio part. So when we try to look at the data now, what kind of data the simulator is able to collect, and what kind of data we want to look into for understanding this driver response on the magnitude level. So for the data, we have several types of longitudinal data, some types of lateral data, and the crash surrogates that we use. Most of them are research grade surrogates. So for the longitudinal data is just the speed, acceleration profiles, the time headways to the lead vehicle, the brake latencies and the brake force, and the throttle of the vehicle. For the lateral data, we want to look at the lane positioning, the steering reversal, the steering entropy, and time that has been used to change their lanes. And if especially in the blind spot warning, whether they were looking at changing the lane and they decided to abort the lane change at the last moment. For the crash surrogates, once we have this data analyzed for all these participants, we will look at if we can go and understand if we can figure out some kind of travel time to collision and post-encroachment time PET values, and also calculate near miss events. So that will be reflected on how smooth the data comes out to be, and minimum gap to adjacent vehicle is easier for us to calculate from this data. So lane incursion at different locations. So there is kind of location blocks that we have used. So we don't want to look at the entire corridor when they are trying to change their lane or not. So we use this location blocks in windows of 5 to 10 seconds when the warning has been relayed to them, whether true or whether false, both kinds of warnings. So once we understand this particular data in terms of how it's looking, we would like to analyze this in cognitive, behavioral, and dispositional ways. And then we want to detect what is the reaction time to the anomaly and what is the attribution target. What do they feel? It feels they have a malfunction at the vehicle. Is it a legitimate safety warning? Some problem with the simulator, or do they have the attribution of whether it is a cyber attack or not? And we want to also see at the trust calibration from the pre-survey and the post-survey, how much that has changed and what kind of behavior changes do they feel based on their identification of their driving behavior style as well. So then we also go with different driving styles subscale and look into their performance interactions, the ADAS familiarity, and that will need to be matched with how much attribution accuracy was there based on the previous responses. And then looking at what are the contrasts between the urban and the rural sites, and then what kind of tolerance level emerges out of these trust levels in this. So for Morgan State, I have not confirmed yet with how much data has been collected for the Clemson counterpart, but for Morgan State, we have already completed data for 90 participants, and so far, none of our participants were able to attribute this to a cyber attack. Some of them attributed it to a sensor glitch, some kind of simulator system malfunction, vehicle system malfunction. So the results appear very significant so far, but the more we get the time to analyze the data and we can come in more confirmation of all the different parameters that we want to analyze for this. These are the anticipated contributions of this particular project during phase 1 and phase 2 at the end of when we deliver both the projects. So we will have a complete STT grounded simulator study for falsified ADAS. We will also be giving conjunction modules for open release. We will be able to validate cross-platform protocols for UC Winroad software, which was used to create these networks in the driving simulator at Morgan. And the Clemson counterparts use the Sim Creator software. So we will be able to see how different of these platforms can look into and record the data across these different parameters and these networks. And then we would also like to see what are the different participant profiles in both the urban and suburban environment coming across as. And then we would like to publish this work in maybe Transportation Research Part F. Some of the agencies that have been in the bracket of stakeholders who would like to listen from this kind of a study. Agencies like NHTSA, FHWA, NTSB. We also have a support letter from MVA, Maryland MVA, Maryland Vehicle Administration for the phase 2, because they would want to help us in taking this research at an education level for drivers during their driving education sessions. So we will make a module for them once we complete the phase 2 at the end of this year. Some of the vehicle manufacturers who especially work with human-machine interface and at the intersection of UX and UI design may find this research useful for them to understand how to design these safety critical warnings and how to increase the confidence and awareness across these warnings when uncertainties arise due to unexpected hacking situations. And some standard bodies which make these OEM based safety standards such as ISO, SAE, and Auto ISAC. And then companies like AAA and the insurance networks, they can also make use of this kind of research to inform their systems better. So we in the phase 2, we are making now these similar networks and interjecting these warnings for forward collision warning and signal phantom signal timings. We have been able to finish that. The next is traveler information messages. We will try to give them misleading information about pedestrian or work zone alert. So all of that we have been able to look at for our phase 2 project. It's still ongoing. And as a toolkit that we will provide once these 2 projects complete is a cyber attack injection modules. It will be open source and they can be used across UC Winroads or Sim Creator in any other university or research center. We will also be designing an attack scenario library, which will be a tech transfer product openly available for anyone on GitHub. And they can look at these standardized scenario specification for any kind of use in their use case or any cross-institution reuse. So they can look at that. And we have got support from M.MVA for this pilot demonstration and in the possibility of looking at it for an education perspective for MVA driver schedule. So that's all from my side. I acknowledge the participants who agreed to drive for 2 hours across our simulators, and Tracer, USDOT for the funding, Morgan State NTC for allowing us conduct this in their premises, and Clemson University for collaborating with us, M.MVA for their support to us throughout this study, and IRB at both institutions, Clemson and Morgan. Any questions?
I have a question personally, but first I would like to thank you for your presentation. So to my understanding, I see that you were doing a driver behavior, collecting data on drivers' behavior under cyber attack, especially for connected vehicle. And the ultimate goal you said is to teach them, make them aware when there is a cyber attack or there's just like, oh, there is a technical issue with the car. So me personally, I think that would be a little bit challenging. For instance, me, who doesn't have any knowledge on cybersecurity, any type of attack. I just come and buy a very nice car, drives it, and something is not functioning properly. I will never think that's a cyber attack. So how can you ensure to make them understand that this is a cyber attack instead of just a technical issue that happened?
That's exactly our intention, to understand whether they are in a informed bracket of people to be able to identify this or not at this level, because our results are by and large indicating towards people not having any kind of intention to attribute this to cyber attack. This actually becomes also a case for increasing awareness about cyber attacks in the transportation driving space. So we that was the first intention to start with. Yes.
So I have a follow-up question, Dr. Swami. So the attacks are changing daily, right? So the new types of attacks. So if you are teaching or making the drivers aware of the most probable attacks, but there are so many attacks that are being generated every day. So what will happen if there's a new types of attacks that are affecting the vehicles, the drivers?
So in the entire gamut of so many vectors that can be possibly targeted in a vehicle, we decided to select only the bracket where the most commonly available ADAS features which are there available in these connected vehicles, and also the kind of attacks which can be induced if we misinterpret or mislead the information from the V2X system, such as our RSU, trying to give an information which may not or may be true. So your question, Dr. Chaudhary, is if we look at these frequently changing attacks and newer attacks coming up. So first intention in these two projects is to look at the 4 most common type of attacks that can happen, and then if the results come out in a direction that we want to explore more attacks, sticking to our connected vehicle system ecosystem, and then sticking to the ADAS safety features and not going beyond that, because there can be infotainment or physical infrastructure or electronic controlling unit or so many different attacks. So we would restrain our capacity to look at the safety features attacks only. We would not like, only the safety features. That's something that we are most concerned with, and that too again in the connected vehicle ecosystem.
Okay, so just another question. So now you're doing it on a connected vehicle where you have human drivers. What happens if it is an autonomous vehicle? So because there's no driver, robot is driving the car. So is there any translation to what you're doing now in the context of autonomous cars?
Yes, it will get more. It will definitely get more complex, because the way the autonomous system attributes it to any kind of happening, it will be different. So it may have way more intelligence in its database than a normal human being, which is maybe sometimes not even aware about the existence of these ADAS system in their vehicles. And sometimes if aware about the ADAS system existence, then they are not aware about possibility of cyber attack, or they maybe read a news about this Jeep Cherokee remote takeover in 2015 and then thought this will never happen to my vehicle, and this is not even something I'll think about. So the way an autonomous vehicle will think about it and respond to it would be very different, and that would be layered very complexly. So at the present moment, we are just focusing on the human response. Maybe in future, Dr. Chaudhary, this can go in that direction.
Right, but I think that what you're learning from this project, you could translate that this is how the autonomous vehicle will recognize an attack, and what are the mitigating measures. So there could be a translation from what you're doing.
Yeah, the recognition patterns can be looked into, but even for that, we will have to work with some kind of OEM that has
Yes.
an EV system ready. Yes.
Right. Thank you.
Thank you.
Okay. So anybody in the audience for another questions?
Any more question? Is there any question on the chat?
No.
You can also write in the chat. So if there is no more question, I would again like to thank Dr. Swami. It was an awesome presentation. It's a lot of things to think about. And I also thank the audience for listening to Dr. Swami and participating in the Tracers webinar series. Thank you all. Thank you. Bye.
Thank you, everyone.
Thank you so much, Tracer, Dr. Chaudhary, and the team at Tracer.